All right, let's dive into one of the most, I think, elegant ideas in all of linear algebra. It's really a story about finding simplicity hiding inside of complexity, about finding the secret blueprint that governs how things change. It's about unlocking a code. I mean, think about it. When a system transforms, maybe it's a bridge under stress or a dataset being analyzed, it can look totally chaotic and unpredictable. But what if? What if there was a way to find the core, stable directions inside all that mess? The properties that don't really change? Well, that's the exact puzzle we're going to solve.
So, here's how we're going to break it all down. First, we'll look at the puzzle of transformations itself. Then, we'll discover these secret own vectors. After that, we'll figure out how to find their special numbers using polynomials, see the incredible payoff of doing all this, and finally, we'll touch on what happens when things get, well, a little messy. Okay, first things first. We've got to meet the main character in our story today, the operator.
You can think of an operator as just a transformation machine. You put a vector in, and it gets stretched, shrunk, rotated, or sheared, and it spits out a new transformed vector. Now, for most vectors you put in, the output looks completely different. It's pointed in a new direction, it's a different length. It's this apparent chaos that we're trying to find some order in. So, how do we find order in all that chaos? Well, it turns out that hidden inside any operator are these special vectors. Vectors that don't get tossed around randomly. In fact, they hold the secret to understanding the entire transformation. And that brings us to the eigenvector. The name really says it all. Eigen is German for own. An eigenvector has its own special direction, a direction that the operator just respects. When the operator acts on it, the vector stays perfectly on the same line. It doesn't get rotated off its axis. This right here, this is the first piece of our secret code. And you know what? Every eigenvector has a partner in crime, an eigenvalue. We usually write it as the Greek letter lambda. So if the eigenvector tells us the direction that stays constant, the eigenvalue tells us how much it scales along that direction. Does it get doubled in length, cut in half, maybe flipped around? That scaling factor is the eigenvalue. This whole beautiful idea is captured perfectly in that little equation, TV equals lambda v. So let's make this crystal clear. On the left, you've got a regular vector. We'll call it W. The operator hits it, and boom, it gets knocked into a new direction, new length, the whole shebang. But look at our special eigenvector v on the right. After the transformation, it's still lying on the exact same line it started on. Its direction is preserved. The only thing that changed was its length, which got scaled by its eigenvalue. And that's the whole game right there. Okay, this is amazing. We know these special vectors and values exist, but how in the world do we actually find them? I mean, you can't just guess and check every single vector in an infinite space, right? We need a system. We need a way to crack the code. Right. This is the big question, isn't it? We know what we're looking for, but we need the how. How do we systematically pull these eigenvalues out of an operator? And the answer, maybe surprisingly, comes from a totally different part of math. It comes from polynomials. Yeah, that's right. Those things you learned about in algebra class, they are the master key to unlocking eigenvalues. So check this out. For any operator, you can build a very special polynomial called its characteristic polynomial. And here's the absolute magic. The roots of that polynomial, the values you plug in to make it equal 0, those roots are exactly the eigenvalues of the operator. So this huge complex problem of finding special directions boils down to something we already know how to do, finding the roots of a polynomial. So finding an eigenvalue lambda tells you something really deep about the operator. It means that this new operator we create, t minus lambda I, is kind of broken. It's not invertible, which means you can't undo it. It's not injective, which means it squishes some different vectors into the same spot, so you lose information. And it's not surjective, meaning there are some parts of the space it just can't reach anymore. Finding an eigenvalue is like finding the exact number that causes this fundamental breakdown. Okay, so we found the code, we used the polynomial key to crack it, we found our eigenvalues and eigenvectors. Why? Why did we do all of this work? What's the ultimate prize for all this? Well, let's set the stage. If you just write down an operator using a normal coordinate system, you usually get a matrix that's just a jumble of numbers. It's messy.
I mean, look at this thing. Can you tell what it's really doing just by looking? How is it stretching things? Is it rotating? It's impossible to tell. The true nature of the operator is totally hidden in this complicated grid. But what if we change our point of view? What if, instead of using our boring old coordinate system, we use a new one built from the operator's own special vectors? It's eigenvectors. And there it is. That is the exact same operator, but when you look at it through the eyes of its eigenvectors, the matrix becomes beautifully, breathtakingly simple. It's a diagonal matrix. All the messiness is gone, and its true nature is laid bare. We can see, clear as day, that along its first special direction, it scales by 1, along the second, it scales by 2, and along the third, by 3. That's it. Simple scaling. The chaos is gone. And this incredible power has a name. We say an operator is diagonalizable if we can actually find enough of these special eigenvectors to build a complete coordinate system or basis for our space. And when we can do that, we unlock this unbelievably simple way of looking at things.
Now, it would be great if every operator was diagonalizable. But, sometimes the code isn't quite that clean.
This is a real thing that can happen. Sometimes an operator is just stingy. It doesn't give you enough unique eigenvectors to build your entire special coordinate system. So what do you do then? Does this whole beautiful idea just fall apart? Well, not quite. We just have to expand our idea of what a special vector is. And that's where generalized eigenvectors come in. You can think of them as the next best thing. While a true eigenvector gets sent right back to its own line, a generalized one might get knocked off course a bit, but it eventually gets sent to 0 after you apply the operator a few times. They fill in the gaps, letting us still find a simple way to represent the operator, even if it's not a perfectly diagonal one. And just to wrap up, there's a really powerful guarantee we have. Thanks to the fundamental theorem of algebra, if we're willing to work with complex numbers, every single operator has at least one eigenvalue, guaranteed. So in the complex world, every operator has a secret code. There's always a thread we can pull on to start unraveling its secrets. So I want to leave you with this thought. This whole idea of finding the unchanging, essential directions inside a complex system, it's so much bigger than just math. It's a whole way of thinking. What's the eigenstructure of your company's culture or social movement or even your own personal habits? What are those simple, core principles that, no matter what happens, seem to govern the whole system? If you can find those, you can understand anything.